Okay, section 3.2. So properties of determinants. Properties of determinants. There are three properties. This is in your ebook. It's Theorem 3 from section 3.2. There are three properties here for a square matrix. First one is if a multiple of one row, well, I'll tell you what, let me demonstrate these three properties in the whiteboard. Okay, let me demonstrate these three properties, and then when you look at the three properties, it'll make a little bit better sense to you. Okay, so let me these three properties are going to save us thousands and thousands of years for computing our determinant. Okay, so what I'm going to do is I'm going to have a matrix A here. So this is section 3.2. Matrix A. And it's going to be 1, 2, 3, 4. Okay, there's matrix A. So I'm gonna put like a Roman numeral 1 because this is going to demonstrate the first property. All right. Or let me see here. Maybe let me just see here one moment. I'll call it A. I'll actually call it A because in the theorem they have properties A, B, and C. So I'll call this example like I'll just put an A next to it. Okay. Now I'm going to put another matrix B to the right. And the matrix B, okay, the matrix B is going to be 1, 2, 0, and negative 2. Okay. So how did we get the matrix? So we did something on the matrix A to get the matrix B. We did a row operation on A to get the matrix B. What was the row operation on A? Let me just, to get B, I'll put this here, to get B, okay, that's right, Solomon, to get B from A, trying to write neatly. Yeah, that's right. You took negative 3 times the first row, added it to the second row, and placed the result, and replaced the second row by that result. Now what I want to do is I want to determine the determinant of A. What's the determinant of A equal to? Negative 2. That's 4 minus 6. And that equals negative 2. What about the determinant of B? Oh, that's -2 also. So does a row operation where we multiply one row by a, like we take a multiple of one row and add it to another row, does that change the determinant? No, it does not. So that is the theorem 3. That's actually the first property. Are there any questions on that? All right, let's do something else here. Yeah. We have 1, 2, 3, 4. I'm going to use the same matrix A. Okay, so maybe I'll try to just separate things a little bit here. Okay. And my matrix B. My matrix B is going to be, in this case, 3, 4, 1, and 2. All right, so how did I get B from A? What did I do there? That's right. That's right, Solomon. We switched rows 1 and 2. And of course, well, the determinant of A, we know that's -2. But what's the determinant of B? +2. Which incidentally is -1 times -2. So if you interchange two rows, you know, this is B here that we're doing. If you interchange two rows, the effect is that the determinant will, it'll introduce a -1. So the determinant, if it was positive, it'll become negative. That's the effect of a row interchange. Are there any questions so far? All right. Well, let's do one more. Because there are 3 kinds of row operations, right? What's the last type of row operation? Scaling. That's right. Very good. Very good. Scaling. So let's say that my matrix B is this matrix. What did we do there? What do we do here to get that that matrix B? What did we do to A? What scaling did we do? That's right. Multiplied the first row by 5. So we took 5 times the first row and put that result in the first row. Replace the first row with that result. So how does that affect the determinant? What's the determinant of B going to be equal to? -10. Good, Solman. Good, Wastina. It equals -10, which you might note is 5 times the determinant of A, which is negative, which was -2. -10 is 5 times -2. Okay, are there any questions? Any questions on the properties here that I'm demonstrating? All right. Well, why don't I'll go ahead then and back to the book then, and we can look at those properties now. Are we good? There. Any questions at all? Don't. Thank you, James. Don't worry. This is going to be on the recording. Don't worry about that. I mean, you did the right thing. Your computer crashed and you came back into the session. So that's I had that happen in another class. There was a storm going on during my class, and power went out, came back on. I went, got right back in to the session. It's all right. So let's go back to the book here. Okay, so now these rules should make more sense to you. Okay, you can appreciate these rules, these 3 rules better. Are there any questions before we move on? All right. Well, let's go ahead here and get to a little example here. So let me bring up a little example. There's a hold on here. Okay, we're going to find the determinant of this 4x4 matrix by row reduction to echelon form. Okay, take a moment to copy that down. Okay, so we want to find the determinant of this 4x4 matrix by row reduction to echelon form. Incidentally, just using regular cofactor expansion, would this be a little bit tedious to do, cofactor expansion for this, to get the determinant for this matrix? And why is that? So you all agree it would take a while to do. Why is that? That's right. That's right, Mikhail. There are very few zeros. So this is sometimes what we call a dense matrix. When a matrix is dense, it means there aren't many zeros in that matrix. So okay, what we're going to do is we're going to get the matrix in echelon form, but and compute and basically compute the determinant as we go. And while we do the row operations, we're going to be utilizing theorem 3 from section 3.2. So okay. So first thing I'm going to do, well, what's the first thing you might want to do here to get matrix A in echelon form? I mean, I'll just mention, I know that we want zeros where the 3, the -3, and the 1 are. I mean, I know that. What might be a good thing to do before that's right. That's right. Robin and Solomon, let's multiply. Let's scale the first row by a half. Okay. So we can get a 1 as a pivot. So what I'm doing then is in computing the determinant, if I do that, I can factor 2 out. And the determinant of A would equal 2 times this determinant here, this 4x4. And notice the first row, I factored a 2 out. The first row was 2, -8, 6, and 8, right? That was your... And I factored a 2 out essentially from all those, but you really aren't factoring. You're using theorem 3C. You applied it once. So the set of new numbers, this is still a determinant. Oh yes. Oh yes. It's not an absolute value. It's a good question, Matthew. The determinant of A equals 2 times the determinant of this 4x4 matrix. It's not an augmented matrix. We aren't doing an augmented matrix here. It's not an augmented matrix. It's just a matrix. It's a 4x4 matrix, and it's not an augmented matrix. I mean, I guess what I'm saying is, one moment. Let me just think on that for a moment. Yeah, it's not an augmented matrix. It's just a matrix. Yeah, it isn't like we're doing, yeah, because well, yeah. Now what we want to do is we want to produce zeros where the 3, -3, and the 1 are, using the 1 here, the 1 here, as a pivot, right? How many row operations does that constitute? 3. Will it change the value of the determinant? So we're going to multiply the first row by -3. Add that to the second row. We're going to take the first row, multiply it by 3, add it to the third row. We're going to take the first row and multiply it by -1, add it to the fourth row. Does that change the value of the determinant at all? It does not. So when you do that, what you've done is you've applied theorem 3a. That's right, Matthew. That's right. You've applied theorem 3a 3 times. And so you get this determinant. So the determinant, let me just the determinant here is equal to this determinant. We applied theorem 3a. I use THM for abbreviation, but I could write theorem, right? Theorem (3a). We applied that 3 times. It didn't change it the first time. For the first row operation, it doesn't change it. Second row operation, it doesn't change it. Third row operation, it doesn't change it. Because they're all row operations where you're taking a multiple of one row and adding it to another row. Okay. So we're trying to get this matrix. Well, we're trying to get this matrix into echelon form, and there's a reason for it. So clearly, the -12 here, we don't want that there. What do we want there where the -12 is? We want a 0. Okay. All right. So all right. So we're going to take 4 times the second row and add it to the third row. Okay, and so that's theorem 3a applied once. Just so you know, I'm not eating. There might be a person nearby who's eating an apple, but it's not me. You know, when I'm teaching, I don't eat when I'm teaching. Yeah, I might have a soda or something, but you know. Okay. Yes, it does, Christy. It sure does. An apple a day does keep the doctor away, and oranges are good too. Okay, now, so we want a 0. We want a 0 in this spot where the -3 is. We're trying to get this in this matrix in echelon form. But generally, I like to use when I'm doing row operations by hand. Is it easier to use smaller pivots or larger pivots? Like, what's our favorite pivot? What's our favorite pivot? Smaller's better, and our favorite pivot is 1, right? Good, Christy, that's right. So what I'm going to do is, I mean, you know, I could take the third row and multiply it by -0.5 and add to the fourth row. But what I'm going to do is I'm going to do a row swap. I'm going to switch the third and fourth rows. And then that introduces a -1. So this determinant, well, actually, James, larger pivots, there's nothing in theory wrong. And actually, for partial pivoting, you want larger pivots. That's something that we're going to learn next week. I might as well make a comment on this. So when you learned about using pivots for row operations, the row reduction algorithm, you tended to like to use small pivots. But in section 1.2, there's a numerical note at the end that says a computer program usually selects as a pivot the entry in a column having the largest absolute value, and that's called partial pivoting. So partial pivoting, and that's something that what we're going to talk about next week, because one of your MATLAB assignments deals with that. Partial pivoting is actually used for LU factorization in MATLAB. And you may have noticed that one student brought it to my attention that he tried to use, like for that section 2.5, the LU factorization. It said, it was the last question in the homework, said use technology, and using MATLAB, you're not going to get the answer. But it's because the section 2.5, the LU factorization you learned was based on I want to say this the right way. The only row operations you were allowed was to add multiples of one row to another row below it for section 2.5, the LU factorization algorithm. You were not allowed to like switch rows, or normally when a computer program like MATLAB row reduces a matrix, like for the LU factorization, it'll do a row switches so that it can use the largest value in a column as a pivot. And so I think what you have to do for that computer exercise is just, do the row operations. I don't think it's that hard to work them out by hand. It might take a little while. And I know some students have done that, because I see some students getting hundreds on that 2.5 assignment. But anyway, just thought I'd mention that. And right, Solomon, no scaling is allowed either for section 2.5 for LU factorization. But at any rate, I wanted to do this. I wanted to do, for this example we're doing in section 3.2, I wanted to demonstrate all three parts of the theorem. And so, okay, so now what we're going to do is we're going to get a 0 where that -6 is. So Matthew, an augmented matrix represents represents a system of equations. A system of equations is represented by an augmented matrix. But if it's just a regular matrix, it doesn't have to be a system of equations. That's the difference. Augmented matrices are for systems of equations. All right, very good, very good. So, okay, so now what do we have to do to get a -6 in the fourth row? We have to take the third row and multiply it by -2 and add it to the fourth row. Would that change the value of the determinant? No. James, I was going to say, the thing with larger pivots, so what you're going to learn is larger pivots actually with computers help reduce round-off error. That's what's going on. That's why larger computers like larger pivots. But as humans, it's kind of hard for us to work with larger pivots. We use smaller pivots. All right, continuing on. We get this. And now look what happens. Look what happens. Now the matrix is in triangular form. This is an echelon form. Triangular form is echelon form, right, for a square matrix. This is now in echelon form. And to finish off, to compute that determinant of that 4 by 4 matrix, what do we have to do? Is it easy to do? Is it easy to compute the determinant of this 4 by 4 matrix? Yes. How would we do it? How would we do it? Just multiply, good, Robin, multiply the values along the diagonal. Because that's what the cofactor expansion is gonna, that's what the cofactor expansion would be. You would find it would just be the product of the values along the diagonal. And so the determinant of A is equal to negative 36. Matthew's question, an augmented matrix must represent a system of equations. Right. Right, and just a regular matrix does not have to represent a system of equations. That's correct. That's correct. Okay. Let me ask you another question here. Are there any questions on this? Are we good so far? That's right. Well, triangular, a matrix is triangular. You don't have, a matrix doesn't have to be square to be in triangular form. It could be, you know, have different number of rows and columns. But if it's a square matrix, echelon form is equivalent to the triangular form. And you know, what if you had a matrix like this? What if you had a matrix like this? What if it were 1, 2, 3, 4? No, hold on. Give me one moment here. What if our matrix were 0, 2, 3, 0, 5, 6, and 0, 1, 4? Let's say we wanted to compute the determinant of this matrix here. And I'll make it a matrix. I mean, the matrix, for a matrix, the determinant has the absolute value signs for notation, but for a matrix, we don't have absolute value signs, right? But what I'm asking is, if I call this matrix just matrix G, what's the determinant of G going to be? Why is it going to be 0? You're right. You're right, Robin. You're right, Solomon. That's right, Robin. Column 1, and Samuel, that's right. Column 1, cofactor expansion along the first column, you're going to get 0. Now, let me ask you this. Let me ask you this. Another question. Does G inverse exist? Does the inverse of G exist? Solomon says no. Solomon says no. Matthew says no. And you're right, because if the determinant equals 0, an inverse will not exist. An inverse will not exist. But maybe I can think of a little. Let me just look at one thing here. I'm looking at the invert. Well, hold on here. One moment. One moment here. Let me think of a. Let me do a little bit. Another example here. Hold on. Let me share the whiteboard. Okay, let's say, because I like to use little examples to help me appreciate the theory. Let's say you had a matrix like this, 1, 1, 3, 3. What's the determinant of A going to be? It's going to be 0, right? Going to be 0. Does A inverse exist? Okay, Solomon says no. But the question is why? I mean, do we even need to? I mean, of course, you have a formula to compute a 2 by 2 inverse, but let's not worry about the formula. Can we use another reasoning why the inverse doesn't exist? I'm thinking of 3 letters. First letter begins with an I. Well, it is an I. Invertible matrix theorem. Very good. So look here at the first column and the second column of A. Are the columns of A linearly independent or linearly dependent? They are dependent because the vector 3, 3 is 3 times the vector 1, 1. Right. So the second vector is a multiple of the first vector. So because of that, the inverse doesn't exist. So the answer is no by the invertible matrix theorem. And so, you know, what I'm trying to say is if a matrix A has a determinant of 0, its inverse will not exist, and that's one of the theorems in section 3.2. It's theorem 4. A square matrix A is invertible if and only if the determinant of A is not equal to 0. And Noah has a good point. There are not enough. These vectors don't span R2. 1, 1, 3, 3. That's another way of thinking about why A inverse doesn't exist. That's good, Noah. The vectors 1, 1, and 3, 3 don't span R2 space. They just span a line in R2 space. All right. So these are just some of the connections that we can make here. And I'll make one comment here before I let you work on 3.1, and I got to get 3.2 posted. And like I said, I don't think 3.3 is going to be hard for you. So I might give a little assignment on 3.3, Kramer's rule, but we'll see. But let me at least finish the thing here. So let me go back to the book. And they have an interesting comment. How long do you think it would take to compute a determinant of a 25 by 25 matrix if the computer utilizes these properties? So originally it would take 500,000 years, right? If we didn't use any determinant properties to help us. But if we use these determinant properties, you know, these row operation properties that we learned at Theorem 3, how long would it take, you think? How much time would it save? Let me see here. An hour? Well, 2 minutes. You're going to save 500,000 years. Look here, the numerical notes. It can be shown that any modern microcomputer can calculate. Well, there's a little more to it than that, but basically it boils down to if you can get the matrix in echelon form, then it greatly reduces your operations, and any modern microcomputer can calculate the determinant in a fraction of a second if you use the specific properties. And they actually show up here that the determinant of a matrix A, if you consider just the row, like don't consider scaling. Like, I guess what I'm trying to say is you can get a matrix in echelon form without doing scaling, okay? And so you wouldn't need to utilize property C. You would only need to utilize properties A and B. And property A, where you multiply one row, one row of the matrix and add it to another row, that doesn't change the value of the determinant. And then property B, interchanging the rows, that introduces a negative. So the determinant of A, and once you get the matrix in echelon form U, you can just write you can just use the product of the pivots to finish off your determinant result. So a general formula in the theory is that a determinant of A could just be computed by taking -1 to the rth power, and rth power stands for how many row interchanges there are, and then multiply by the product of the pivots in U. And using this approach, a computer, most computer programs use this approach to compute the determinant of A for a general matrix, and any modern microcomputer could calculate a 25 by 25 determinant in a fraction of a second, because about only 10,000 operations are required. That's what it says in the numerical note. Okay, so you see how many think that's absolutely cool? Yeah, Matthew likes that. How many are liking these rules, for determinants in 3.2? Okay, great. All right, well, let me stop the recording here.